Okay, carry on with an example, 14.8. And here we're going to look at both power and efficiency. Okay, so we've got this crate. We have this pulley system. Got a little pulley there. Right, that cable is attached to the top beam there. And there's a pulley, and this pulley is attached to a motor. Okay? The motor M of the hoist shown lifts the 35 kilogram crate C so that the acceleration of point P is over here. So if we just redraw this, okay, into the motor. Okay, there's the motor, and that goes up. It's attached like that, and you've got the crate there. Okay, so this is point P. So point P has an acceleration. So acceleration of P is 1.2 meters per second squared. Determine the power that must be supplied to the motor at the instant P has a velocity of 0.6. Okay, so we got acceleration information of P and the velocity of P. Okay, now we'll get to this this idea of supplied to the motor. So one thing you need to understand is that we have power that's coming into the motor and power that the motor is supplying. So this motor is powered somehow, generally by just plugging it in, right? Okay, so that you've got some power coming to the motor, and then the motor has losses inside because of friction, so there's losses inside, and then the power out that the motor can deliver is generally less than the power that, not generally, it's always less. It's always less than the power that comes into the motor. Okay, but we'll get back to this. Okay, so now what do we want to do? What's our baseline? We know that power is force times velocity. Okay, so we know what the velocity at P is. So the question is, determine the power that must be supplied to the motor at the instant P has a velocity of that. Neglect the mass of the pulley and the cable and take your mechanical efficiency to be 0.85. Alright, so now let's just think about this. If we focus on, actually I'm going to focus on the motor now. The motor you take and you plug it into the wall. Okay, you plug it into the wall and it has a power in to the motor. Then this motor is now, there's point P, right? This motor is now pulling. It's applying a force, a tension. Okay, it's applying a tension. So if I know what the force at point P is and I know the velocity at point P, I can work out P out equal to force times velocity. Alright? Then, once I've got P out, I can use my mechanical efficiency to determine, this is P times velocity. Then, if I've got my mechanical efficiency and I've got my P out, I can calculate P in, which is the power that must be supplied to the motor. Okay, so what is this power that must be supplied to the motor? Alright. So, we have the velocity, we're looking for the force at P. What is the force at P? It's a tension in the cable. How are we going to find that? Well, we could draw a free body diagram of this crate, which we do here, and we can see that upwards we've got T, and down we've got weight. Okay? So, there's our free body diagram there. 2T is up, and down is weight, and we know that it's accelerating, so we have some of the forces in the y direction is mass times acceleration in the y. We have, and down is positive, so minus 2t, 2t upwards, that's minus. Down we have mass times gravity is equal to mass times acceleration of the crate. Okay? I hope we're all happy with that. Now, we don't have tension, and we don't have the acceleration. So the next thing that we could do is, let me change the color here. We could carry out kinematics. Okay, absolute dependent motion. We could take that as our datum. That becomes SC, right down to that crate. And then we've got SP, right? So this is the position of the crate. That's the position of point P. Then we know that 2 times SP, that plus that, plus, mistake. 2 times SC plus SP is the total length. If we take the second derivative, we're going to have 2 times AC plus AP is 0. And that's what we get there. All right. So now, what are we going to do? We know that the acceleration of point P was 1.2. Okay? So AC is then minus AP over 2, and its AP was 1.2 over 2, so minus 0.6. This is what we get for the acceleration of the crate. Acceleration of crate is minus 0.6, meaning it's accelerating upwards. Okay, meters per second squared. Okay? So now we can go back to this equation. We can go back here. We plug in our acceleration of the crate, which is minus 0.6, which we do there, and we calculate T. I want to ask you again, why are we calculating T? Because power out is force times velocity, and our force at point P is the tension that's in the cable. Okay? So we do this. This is power times velocity, or tension times velocity. 182 times the velocity is 0.6. Very good. This is now power out. This is the power that the motor is delivering. Okay? Now we need to find, what do we need to put into the motor in order to get this? Well, we know that efficiency is P out over P in, and we know that efficiency is 0.85. So P in is then P out divided by 0.85, which is 109.3 over 0.85. Is this going to be higher or lower? If I divide by 0.85, will it be higher than 109? Yes, 129 watts. I hope that makes sense, guys. Again, you need to look at this critically. Your power in will always be higher than your power out. Okay? Power in is always greater than power out. So if you go and do this calculation and you get your power in to be lower than your power out, or your power, that you're getting more power out than putting in, then you've made a mistake. Okay? Alright, hope you learned something. Cheers.